Okay, so we want to graph this rational function 2x squared minus 3x minus 5 over x squared plus 1. So we're just going to go through all the things and figure out what's going on this function. So we're going to just start out by finding the y-intercepts and the x-intercepts. To find the y-intercept, you just put in 0 for x and see what you get. So g of 0 is going to be negative 5. So we'll go ahead and graph that on our graph. That's our y-intercept. For our x-intercepts, we're going to have to set the numerator equal to 0 and see what values of x will give us 0 for this function, because the only reason we're only using the numerator is because the denominator can't be 0. We can't allow that to be 0. So the only way this function will ever be 0 is if the numerator is 0. So that's what we're going to check. So 2x squared minus 3x minus 5, set it equal to 0 and see what you get. You can factor this like this, and so you can see that either 2x minus 5 is 0 or x plus 1 is 0, which means that x would be 5 halves or negative 1. Those are our two x-intercepts. So we're going to put those on the graph. Now we're going to look for a vertical asymptote. A vertical asymptote happens when the denominator of the function is equal to 0. That's a bad place that you don't want to go. So we can set that denominator equal to 0, and we immediately see it can never be 0 because x squared is positive and 1 is positive. That is never going to be 0, so there will not be a vertical asymptote. Okay, now a horizontal asymptote. If we look at the numerator and denominator of this function, this is what we want to do. We want to see what the degree of the numerator is and what the degree of the denominator is, and that's going to tell us about our horizontal asymptote. So you can see that for g of x, the degree of the numerator is 2, and the degree of the denominator is 2. They have the same degree, and therefore the leading term is going to dominate the numerator, and the leading term is going to dominate the denominator. So the numerator is going to be dominated by 2x squared, and the denominator is going to be dominated by x squared. So 2x squared over x squared is giving us 2. So y equals 2 is our horizontal asymptote right there. And now that we know that there is a horizontal asymptote, we're going to ask the question, does the graph cross that horizontal asymptote? Because remember, the graph can cross a horizontal asymptote. It cannot cross a vertical asymptote. So the way to figure out if it ever crosses that horizontal asymptote is to see if this function can ever equal 2. If it can, then it'll hit that asymptote. So we're going to set the function equal to 2. 2x squared minus 3x minus 5 over x squared plus 1 equals 2. Multiply both sides by x squared plus 1 and solve for x. So it can equal 2 when x is negative 7/3. So at x equals negative 7/3, this function will hit that horizontal asymptote and it will go over it. All right, now we're going to check for symmetry. G of negative x, if you put in negative x into this function, and I'm just going to go ahead and do that to make sure we know what's going on here. So if I put in negative x into that function, I'll have 2 times negative x squared minus 3 times negative x minus 5. And then in my denominator, I'm going to have negative x squared plus 1. And so that's going to be 2x squared plus 3x minus 5 over x squared plus 1. And so you can see that that does not equal f of x or g of x. It's not the same as g of x, and it's not the opposite of g of x. So that means that it doesn't have symmetry about the y-axis, and it doesn't have symmetry about the origin. Because if g of negative x is equal to g of x, then it's going to be symmetric about the y-axis. If g of negative x equals the opposite of g of x, so if g of negative x were equal to the opposite of g of x, then you'd have symmetry about the origin, but it's not. It's not equal to the opposite. So not even, not odd. Okay, so for the slant asymptote, remember the degree of the numerator would have to be exactly 1 more than the degree of the denominator, and that's not happening. So there is no slant asymptote. All right, so now we're going to look at how the function is behaving on these intervals. Okay, we're going to look from negative infinity up to negative 7/3. And the reason we're going to look at that negative 7/3 is because something's happening there. It's crossing the asymptote. So if we pick an x value between negative infinity and negative 7/3, we can pick anything we want. Negative 3 would give us 11/5. So if I put that point on my graph, negative 3, 11/5, you can see that it's right there above the asymptote. So that means that from negative infinity up to negative 7/3, this function is above the asymptote. All right, now we're going to check from negative 7/3 up to negative 1, which is a 0 of this function. So at that point, it's going to cross the x-axis. So we're going to see what's going to happen there. So if we look from negative 7/3 up to negative 1, we'll check a point, any point. We'll try negative 2, and when we do that, we will get 9/5. So negative 2, 9/5 is right there, which means that for all the points between negative 7/3 on the x-axis and negative 1 on the x-axis, this function is going to be positive. It's going to have a positive value. So it's going to stay above that x-axis until it gets to negative 1. So that's what that part of the function looks like. And just to make sure you know, this area right here, that function is approaching. It's meant to be approaching the asymptote. So it doesn't look all that great, but it's supposed to be approaching the asymptote. So we had our 0 at negative 1, and the next 0 is going to be at 5/2. Remember over here when we found our x-intercepts. So we're going to go now from negative 1 up to 5/2 and see what the function is doing. Pick a point. Could be 1, 2, anything in there. 0 also works. So 0, negative 5 is on this function. And so that means since it's negative 5, since you get a negative 5 there for the value of the function, that means that the function stays below the x-axis all the way from negative 1 up to 5/2. So in this interval, the function is always negative. The value of the function is always negative below the x-axis. So we go down and back up again to the 0, and then from 5/2 to infinity is our last interval. If we try a point in that, we could pick 3. If we put 3 into the function, we get 2/5. So 3, 2/5. 2/5 is positive, so that means the function will be above the x-axis for the rest of all the way to infinity. And that means that it has to approach that asymptote from below. Okay, so here we have h of x equals 2x squared plus 9x plus 4 over x plus 3. So we're going to start out again by finding our y-intercepts and our x-intercepts. So to get your y-intercept, you plug 0 in for x. H of 0 is equal to 4/3. And so there is a 0. The y-intercept is 4/3, which is right there. Then our x-intercepts, we have to set the function equal to 0 and see what x would be. And the only way for this function to ever equal 0 is for the numerator to be 0. The denominator can't be 0. So we will check the numerator and make it 0 and see what values of x are going to make that happen. And so this will factor like this. And so that means that x would have to be negative 1/2 or negative 4. So those are the two x-intercepts, the zeros of the function. So we graph those. Now we're going to look for vertical asymptote. Vertical asymptotes happen when the denominator is 0. So when x plus 3 is 0, x is negative 3. So there is a vertical asymptote at x equals negative 3. Horizontal asymptote. For that, we look at the degree of the numerator and the degree of the denominator. The degree of the numerator is 2. The degree of the denominator is 1. Therefore, the numerator dominates, and this function just gets bigger and bigger without bound. So that means that there is no horizontal asymptote because it's just getting huge. It's not going to ever be stopped. So no horizontal asymptote. All right, slant asymptote. We're going to look for a slant asymptote because the degree of the numerator is exactly one greater than the degree of the denominator. And that's when you can possibly have a slant asymptote. So we're going to have to divide the numerator by the denominator. So we'll divide by x plus 3, and x goes into 2x squared, 2x times, and multiply 2x squared plus 6x, subtract, and you've got 3x plus 4, and then x goes into 3x 3 times, multiply, and you get 3x plus 9, and so you have a remainder, but the remainder doesn't matter. You just want to look at this line, y equals 2x plus 3, and graph that. So the y-intercept is 3, the slope is 2, so that's what the slant asymptote looks like. Okay, so one thing that we didn't talk about in class today is that you can cross a slant asymptote also. You can't cross a vertical asymptote, but you can cross a horizontal asymptote or a slant asymptote. To find out if the function crosses this slant asymptote, you would again set the function equal to the slant asymptote and see if it can equal that. So we've got our function 2x squared plus 9x plus 4 over x plus 3. And we want to see if that can be equal to 2x plus 3, the slant asymptote. So we would multiply both sides by x plus 3, and we'd have 2x squared plus 9x plus 4 is equal to 2x squared plus 9x plus 9, and 4 does not equal 9, so it does not cross the asymptote because the function can't equal the asymptote. Okay, so now we'll set up our intervals to figure out what's going on here. Where do we draw the curves and what do they look like? Okay, so that first interval is going to go from negative infinity up to -4, the first 0. All right, so if we look there and we try -5, because that's in that interval for our x, plug that into the function and you get -4.5. So you can see that point, -5, -4.5, that's going to be on our curve. That is below the x-axis, and that's where it's going to stay for that interval from negative infinity to -4. It's always below the x-axis because that's what the y value we get is negative, so below the x-axis. And then our next interval is from -4 to -3, from that 0 to the first asymptote. And there, if you try a point like -3.5, plug it into the function, you get 6. And that means that from -4 to -3 on the x-axis, the function is positive. And it looks like that. Okay, so the next interval we're going to look at is the interval from -3 to the second 0, which is -1/2. So between -3 and -1/2, you could try the x value of -2. If you put in -2 for x and you plug that into the function, you're going to get -6 for y. So that point, -2, -6 is right there. So you can see that on the interval from -3 to -1/2 on the x-axis, you're going to be negative. Your value of your function is going to be negative below the x-axis. So you're going like that. All right, now you're going to look at -1/2 to infinity is your last interval. And so you can try 0. That's in that interval. So if you put 0 in for x, you get 4/3 for y, and there's that point. So you know that your curve is going to go through that point. It's going to be positive, and it's just going to keep on being positive and approaching that slant asymptote like that. Okay, now we're going to look at an application. It says linear model of the cost for a business to manufacture X items is C of X equals MX plus B, where M is the variable cost to produce an individual item and B is the fixed cost. The average cost per item manufactured is the sum of all the costs divided by the total number of items produced. This is given by the equation C of X, C bar of X, is equal to C of X over X. Okay, so let me just say that again. If you have a linear model for the cost it takes a business to manufacture X items, and that model is C of X equals MX plus B. So if you're going to make, 100 items, C of 100, if you put that into that function, it's going to tell you how much that's going to cost you to make that many items. So this is the function that goes with some company that makes a certain number of items and it costs them a certain amount. Where M is your variable cost, remember, like, so if you're selling lemonade, it's the cost to make a cup of lemonade. And then you've got some fixed costs, B, which are like your rent and stuff like that, where that part doesn't matter how many cups of lemonade you make, you still have to pay it every time. It's the same. So now they're talking about the average cost per item manufactured. So how much is it costing you per item to make if you include all the costs that are happening? So the fixed cost, the variable cost, everything. You would look at that whole cost function, whatever that is, C of X, and you would divide it by the number of items you made, which would be X. So let's look at this example. A cleaning service cleans homes. For each house call, the cost to the company is approximately $40 for cleaning supplies, gasoline, and labor. The business also has fixed monthly costs of $300 for phone service, advertising, and depreciation on the vehicles. So we're going to write a cost function to represent the cost C of X in dollars for X house calls per month. All right. So that is C of X, is equal to MX plus B, where M, those are your variable costs. So that's your $40. Every time you go to a house, you have to spend $40 on cleaning supplies, gasoline, and labor. So that is per house you clean. That's a $40 per house amount of money that you have to spend. So 40 times the number of houses you go to. And then you've also got your fixed costs that you have to add to that, which is your phone, your depreciation on vehicles, your advertising every month. So that's something you have to add on there. So this is the cost function. We learned about these last chapter. So that's the regular cost function for this situation. Now, what about the average cost per item? So we want to write the average cost function that represents the average cost, bar C of X, in dollars for X house calls per month. So in that case, that C bar of X, that's going to equal your cost function, 40X plus 300, divided by how many house calls you made, which is X. So you're adding up all your costs now and dividing by the number of house calls, and that's going to give you your average cost per house call. So we're going to evaluate C bar of 5, C bar of 20, C bar of 30, and C bar of 100. Okay, so if we put 5 into that function, that's going to be 40 times 5 plus 300 over 5. So that's going to be 200 plus 300 over 5, which is 500 over 5, which is 100. So $100 per house. That's your average cost per house call if you only make 5 house calls a month. So it's pretty expensive to clean only 5 houses a month. So if you do C bar of 20, if you clean 20 houses in a month, then you're going to do the C of X over X to find out your average cost per house call. So that is going to be 40 times 20 this time, plus 300 over 20. So that's going to be 800 plus 300 over 20. So that's 1,100 over 20, and that's going to be $55 per house. So that's cheaper. The more houses you go to, the less it's really costing your company per house. Okay, if you get up to C bar of 30, and I'm out of room here, so I'm just going to stick it up here somewhere. So if you do C bar of 30, and you clean 30 houses in a month, you're going to have 40 times 30 plus 300 over 30 this time. So that's going to be 1,200 plus 300. That's going to be 1,500 over 30, which is going to be $50 per house. So you can see that the more houses you clean, the better. And then if you put in 100, you're going to have 4,000. You're going to have 4,000 plus 300, so 4,300 over 100, which is going to be only $43 per house. Okay, the cleaning service can realistically make a maximum of 160 calls per month. However, if the number of calls were unlimited, what value would the average cost approach? What does this mean in the context of the problem? You can see that as X gets bigger, as the number of houses we're visiting gets bigger, the cost per house is going down. By the time we get to 100 houses, the cost is down to $43. They say that the maximum number of calls you could realistically make in a month would be 160. So let's just look and see what that would be. So the function we're looking at, remember, C bar of X, that's a rational function, right? Okay, so let's look at this function in terms of remembering what it means to find a horizontal asymptote. Because if we're looking for a value that this function would approach, we are looking for a horizontal asymptote. Is there some value that this function approaches, but never gets to, or possibly gets to, but still approaches? We have a linear function on top and a linear function on the bottom. We have a x to the first power on top, x to the first power on the bottom. The numerator is of degree 1, the denominator is of degree 1, and when we have our numerator and denominator have the same degree, that means the numerator is going to be dominated by 40x and the denominator is going to be dominated by x. So this function is going to approach 40x over x. This is going to be the horizontal asymptote, which is 40 over 1. So this function approaches 40. So that means that as you do more and more and more houses, if you could do all the houses you ever wanted to, you could get that cost down to $40 per house. But once you do that, it's never going to get any lower than that. So you can see the graph. As the number of houses you clean gets bigger, the cost comes down, but it's never going to get below $40 because that's the horizontal asymptote we were just talking about. The function will never go below that. And so no matter how many houses you clean, you're never going to get below $40 per house based on that algebra.